Right, okay, so quite a few people have said that they want to go over at equilibrium, and probably, if I'm being honest, one of the trickiest things in C3 used to be in C2 a little bit, but now it's in C3. In C2, to be honest, all you need to know about equilibrium is just that this sign here indicates that it's a reversible reaction. Beyond that, really, bit about heating equilibriums. That's all you really need in C2. But in C3, the details significantly more. So what we're going to do, we're going to explain a few things about what an equilibrium is, and then what we'll talk about then is what happens when you start to add um, increases to temperature, or you change the pressure, or you start to you start to change things like concentration. So first and foremost, hopefully you know that when you are dealing with an equilibrium, this sign here indicates the reaction is reversible. So that tells you that the reaction is reversible. It means that when nitrogen and hydrogen react together, make ammonia, what can happen is the ammonia can then break back down and make nitrogen and hydrogen. Seems simple enough, it is. So let's say at the start you start off with 100% of these two and 0% of that. And over time, he might settle out at an equilibrium, let's say, which is 75% or 72%, sorry, of that side and 28% of this side. Now that will stay like that then, and that's now what we call at equilibrium. A lot of people think that to be at equilibrium something has to be 50-50. That's not true. What happens at equilibrium is once you've reached that equilibrium, the definition of it's just wrote down here at the bottom. The rate of the forward reaction is equal to the rate of the backward reaction, and all the concentrations remain constant. Lots of people in the exam see um, concentration, or will say, sorry, that concentrations remain the same. You can't write that in an exam, that's wrong. And the reason why it's wrong is because when you say the concentrations are the same, you're effectively saying that these two numbers are the same as each other, and that's not true. They're not the same. They're obviously different numbers, but they are constant. So no matter what happens now, this reaction will stay with 72% nitrogen and hydrogen and 28% ammonia. It'll stay at equilibrium. One other thing to note, if you're asked to define the term dynamic equilibrium, these are the two marking points you would need to say for the examiner. So you'd need to say rate of forward equals rate of backward, and all concentrations remain constant. What you've also got to be aware of is that the reactions keep happening. So you might have, you might have a little bit of forward reaction happening, a little bit of backward. It's like being on a treadmill. Things keep happening, but when you're looking from the outside, it looks like nothing's moving. And it's a similar scenario with these kind of reactions. So hopefully we can go on to explain what happens when you change various different things and how that impacts on the equilibrium. Right, concentration is the first thing I'm going to deal with. If I increase the concentration of a substance, then the equilibrium will shift in such a way um, to remove what I have added. So let's look at this example here, which is an equilibrium you've probably never seen in your life, but the principle is pretty simple. If I decide I'm going to increase the concentration of this, so this here is ammonia, I'm going to increase the concentration of that. Now when I do that, the equilibrium, because I've put more of this in, the equilibrium will attempt to remove it by moving to the opposite side, so it'll go to the left hand side. And the reason why it does that is because it's trying to oppose the change. So what I've done, it's trying to sort of oppose that and remove the ammonia that I've put into the mixture. And if you were asked in the exam what would happen to the equilibrium if I increase the concentration of ammonia, you'd say the equilibrium will move to the left hand side in this case to oppose the change and remove the ammonia that was added. Vice in the other way, or vice versa should I say, if I decide I'm going to remove something, then the equilibrium will try and make more of it. So if I go over here and say, right, I'm just going to start to remove this ammonium sulfate here, then the equilibrium will attempt to replace it. So if I start taking the ammonium sulfate out of the mixture, the equilibrium would then try and replace that and put it back. And just like we said before as well, when you take, say for example here, the sulfuric acid, if I decide, right, okay, I'm going to remove some of that, then the equilibrium will try and go to the right hand side to make more of it to oppose the change. So the equilibrium is a little bit like a naughty child. It'll do exactly what you tell it not to do. So if you do something, it'll do the opposite. It'll oppose whatever you do.